Aloha class, it is Bears Packers tonight. Let's go Mac. 2 interceptions, touchdowns. If you're a Packers fan, remind me tomorrow in class to take away 100 points from your team. All right, here we go. Section 3.9, derivatives of exponential and logarithmic functions. All right, if we're looking at the AP and the course catalog, that is topic 2.7. We've already done cosine and sine, but now we're going to do e to the x and the natural log of x, which we remember back from our pre-calc days, those are inverses of each other, and we just got done talking about inverses. If I use this hand, it covers it. This hand does not. Swim move. Cleo Mac. All right, here we go. 3.9, derivatives of exponential and logarithmic functions. We're going to get this bad boy started with deriving what the derivative of e to the x is. And then able to do that, we need a result. Okay, so what I would love for you to do is hit pause and graph that bad boy. Okay, hopefully you did that, and you are going to get that result right there. And if you check the limit as we approach 0 from the left is 1, from the right is 1. So a rule that we can use for the rest of the year, kind of like the smiley face over smiley face, is the limit of e to the h minus 1 all over h is equal to 1. All right, so you guys can use that from now on. Okay, now here we go. Derivative of e to the x and the derivative of e to the u, okay, where it involves somewhat of a chain. Now, what a lot of textbooks fails to mention here, and I want you to write this down. If we really take the derivative of a power function, or exponential function like e to the x, it's actually equal to e to the x times the natural log of the base. Now, the natural log of e, if you remember from pre-calc days, is just 1, and that's why we kind of just drop it for that problem, okay? But I want you to remember, because there's another one you have to remember, is what happens if I have something other than an e. Let's say it like is 7. So we'll say it's like a to the x, okay? Something other than this fancy dude e, right? 2.718. That is equal to a to the x. It's kind of like you just rewrite it, but then times the natural log of a. And the natural log of a is not 1 in this situation, so we've got to keep that. So that's an important thing to remember going forward, okay, class? Just like this one, it's technically e to the u times the natural log of e, and then, right, like anything, we have to chain, okay? So that's technically the formal definition, all right? The proof of this can be done using the original definition of the derivative. So let's go ahead and do that. This is really good practice going back to our original definition of the derivative, which would be the limit as h approaches 0 of, remember, our function to the x plus h minus our original function all over h, right, class? And then I can do some simplification here. A lot of us forget these rules, so pay very close attention. That would be e to the x times e to the h minus e to the x all over h. Hopefully you notice both of my terms in the numerator have a e to the x in it, so I can factor that out. Okay, and I get that result. And then I can use the limit of a product is a product of my limits. So I'd get e to the x times the limit as h approaches 0 of e to the h minus 1 over h. This piece here, I have nowhere I can put a 0 in for h, so my answer is just e to the x. This piece here is that result that we used earlier, which is equal to 1, and thus it's e to the x. And you know what's really cool, class? We just got done with some graphing, right? And hopefully we know what e to the x looks like. Okay, it's that. It always has, believe it or not, a positive tangent slope, right? Instantaneous rate of change. And believe it or not, hit pause and try to draw the derivative of that, and you get the same exact thing. Oh, snap! No wonder why the derivative of e to the x is e to the x. Pretty cool and neat if you really think about it. All right, let's go ahead and do some of these derivative guys, okay? Let's see. Booyah, booyah, booyah. All right, so we're going to take the derivative of e to the 2x minus 1. Well, guess what? That is simply e to the 2x minus 1, but I have an inside, right, class? So I'm going to write this longhand this time. So then I'm going to have to take the derivative of that inside. So my answer would be e to the 2x minus 1, don't you dare touch the inside, times the derivative of 2x minus 1, which is 2. And remember, there always should be a times the natural log of the base. So natural log of e is 1, but we don't write it because it gets a little tedious. All right, let's try this bad boy. I don't know if I can see it clearly. I think it says e to the negative 3 over x. Okay, so for one, I should probably rewrite this problem before I get it started. That'd be e to the negative 3x to the negative 1. Right, class? I should definitely rewrite that. I wouldn't want to do some quotient rule unless I like my low d high. All right, so let's go ahead and take the derivative of that boy. It's an e, it's an inside. I'm not going to touch the inside. So the derivative of e to the something is we just rewrite it. But then I have to take the derivative of that inside, which would be a power rule. Drop that negative 1. I get 3x to the negative 2. Booyah, problem done. Could I simplify and make that a little bit prettier? Sure, I could. Okay, here we go. F of x equals the natural log of x. Now we open up to this bad boy. Do we know what that graph looks like, class? Graph it right now. Hit that pause button. But e to the x and the natural log of x are inverses. So if they're inverses of one another, it would look like that. Now, challenge yourself. Let's go. Ooh, snap. Challenge yourself. The derivative graph. What would that look like? Hit pause. Okay, it's always increasing. If it's always increasing, believe it or not, hopefully you got a little graph that looks like that. And believe it or not, that's very similar to another graph, which if I drew both pieces, would be 1 over x, which actually happens to be the derivative of the natural log of x. All right, so here we go. Derivative of the natural log of x. Boom. What if there is more than a plain old x? Boom. You kind of probably already knew how to do it. So let's go ahead and practice some of these bad boys. Ooh, that's actually, I am so sorry, but I love proving this stuff. You get to higher level mathematics, you get to prove this stuff like crazy, and it actually becomes really, really fun. Actually, you know what? Let's save this guy for class. Make sure I do it. I challenge you to see if you can somehow get that on your own, okay? If not, we're going to keep this video rolling. All right, here we go. Let's take the derivative. Let's find y prime. Y prime. Well, it's a natural log is on the outside, a 2x plus 2 on the inside. So my outside's natural log, and what do? Believe it or not, class, it's just 1 over. 1 over that something, don't you dare touch it. But then you take the derivative of that something, which is just 2. And these problems you can usually make prettier. Everything has a 2 in it, so I could get crazy and booyah. There we go. Let's do the next one. F of x. So we're going to do f prime of x. F prime of x is equal to my outside is there, my inside is tangent. If my outside's natural log, it's 1 over the something. Don't you dare touch that something. But then you have to take the derivative of that something, and we get secant squared x over tangent x. There's actually some simplifying you could do right there. See if you can figure it out. Okay? Keep on rolling. Uh-oh. Oh no, SpaghettiOs. A lot of my pre-calc students struggle with this box. It's a quick refresher. These make these problems very okay to deal with. Make sure you know every single one of these guys, and I'm going to show you how they become very helpful. Hopefully everything I do right now does not seem foreign, but it's going to help make some of these difficult log problems very doable. All right, here we go. Find the derivative. So let's go a little dy dx. However, you know what? I might rewrite that as log base 5 of x to the 1/2 first, because we like our rational exponents and we like our negative exponents. The next thing I'm going to do is, we don't really have a derivative of this log base. So what I'm going to do is I'm going to use my change of base. So if you notice, everything I am doing right here is just rewriting this problem, which is the natural log of x to the 1/2 over the natural log of 5. And then I'm going to do something else. I haven't even found the derivative yet. I'm just going to rewrite this. That's y equals 1 over the natural log of 5 times the natural log of x to the 1/2. Now, why would I do that? Because this dude right here is just a constant, okay? And let's find the derivative. dy dx is equal to constants just kind of hang on, right, class? They just kind of hang on. And then I have to take the derivative of the natural log of x to the 1/2. And it's a natural log. That's my outside, right, class? That's the outside right there. So it's just 1 over. Don't you dare touch that inside. But then I have to take the derivative of that inside, which would be 1/2 x to the negative 1/2. Obviously, some big time cleaning up I could do there. I'm going to keep it. I guess I'll probably go up here. So that would be that. Where's the 2? The 2's on the bottom, right? So I can put that in front so it looks pretty. And then x to the 1/2 times x to the 1/2 is x, but then that looks like 5x. So I should probably rewrite the answer like so. Right? If that's a multiple choice question, that is how it will be written. Okay, let's go to my second example. Find the, oh snap. That's like an e to the x. And do you remember what I said earlier? Don't look back, hit pause. See if you can get it right. Be really impressed if you do. Dy dx, that is not e to the x, that's 2 to the x. So it's 2 to the x times the natural log of 2. Here you have to have it, right, class? In the e to the x problems, it's always the natural log of e, which is 1, so we don't actually write it in those problems, okay? I almost skipped example 9, and 9 looks super fun. So let's go ahead and look at 9. Oh, snap, it's just a whole bunch of things. It's like you got a function there, a function there, and a function there. Let's get crazy. Okay, g prime of x is equal to the derivative of e to the 5x. Right, that'd be e to the 5x times the natural log of e, which is 1. We're not going to write it. That's crazy. Times, that's more than a plain old x over there. So I have to chain it, which would be 5 plus. Now that's 7 to the x, which would be 7 to the x, but it's always times the natural log of the base. I need it there because that is not 1. And then my last piece is a natural log, an outside and an inside. So it's 1 over, don't you dare touch the inside, and then multiply it by the derivative of the inside. So I could clean this up a little bit. What would it look like as a multiple choice? It would look like that, plus, it would leave it as 7 to the x natural log of 7. And then this last piece I could write as 3x squared over x cubed plus 4. Some of you want to cross out some x's here. Don't you dare. Did I look like Khalil? All right, here we go. Let's keep on rolling. Logarithmic differentiation. Oh my gosh, so fun right now. Okay, technique used to rewrite a function as one or more natural log functions in order to find its derivative. When do we want to use this? When the function has when you see. Okay, so I'm going to have you fill in some notes right now. When the function has many terms, okay, that are products or quotients. Okay, so when you see products or quotients and some logs, you want to do that. Okay, and that kind of fits in for both of those guys. And we follow these steps. Take the natural log of both sides of the function, use properties of logs to expand, implicit differential. Oh my gosh, and then so, this sounds like everything we've learned ever in math. How fun. Let's do this. Let's go. Give me them toes. All right, here we go. Oh, I got a quotient. Oh, it's looking crazy. So what's step 1 say? Take the natural log of both sides. If you notice, I'm not even finding a derivative yet. So let's go. The natural log of y is equal to the natural log of x squared plus 1 to the 1/2 power all over x plus 1 to the 2/3 power. I hope it says 2/3. It's kind of hard to see on this screen. Let me check my notes here. Is it 2/3? Booyah, it is. All right, whew. What do I do now? Well, I'm not even going to take a derivative yet. I'm still going to expand. That'd be the natural log of y. And if I expand this and you don't understand it, I better see you tomorrow morning. This is pre-calc, okay? Natural log, and I'm going to expand. If it's multiplication, it's a plus sign between them. If it has a exponent, I can drop the exponent out in front. If it's division, it's a minus sign in front of it. Once again, if it's an exponent, I drop it out in front. If that step that I just wrote down looks foreign, I will see you mañana. Okay? Now, watch how nice it is to take the derivative. The derivative of the natural log of y, that's an inside and an outside. So it's 1 over don't you dare touch. What's the derivative of y? It would be 1, but I'm doing it implicitly because I'm doing it with respect to x. Done. Okay, the natural log of x, that's just 1 over x. Take the derivative of x. The derivative of x is 1 dx dx, so it goes away. Plus 1/2 is a constant, so it's 1/2. And then I have a natural log, that is 1 over, don't you dare touch the inside, and then take the derivative of the inside, and then my last is minus 2/3 because it's a constant. 1 over, don't you dare touch the inside, times the derivative of the inside. Let's clean this bad boy up. Booyah, booyah. Okay, and then I get a dy dx because I think it says at the end you multiply both sides by a y, so I'm going to put that y out in front, and then I get 1 over x. Let's clean this up, plus x over x squared plus 1 minus 2 over 3x plus 1. Boom. And then I've got that y. And then I think it says earlier, it sure does, we don't want a y in our final answer. So I'm going to take this. I'm not writing it all, but you plug it in there. And then you have dy dx all in terms of x's. And you don't have to distribute that in. That would be sufficient for a 100% good correct answer. All right. Once again, the toughest part of that problem, believe it or not, is pre-calculus, is do you know all of your log stuff? Okay, here we go. Example 8. Oh, snap, that looks kind of fun. Look, I have a function to a function. Now, why do I say a function to a function? Because the inside and the outside both have an x in it. So here's a technique. This would be an example of take the natural log of both sides. But what I am going to do first is I am going to let f of x equals y. Okay, to kind of help myself out and not make it too confusing with that notation. So that's the inverse tangent of x, and then it's e to the, oh, I can't see it. Let me look at the screen. It's e x cubed minus 4. So it's x cubed minus 4. But it's a function and a function, so I'm going to take the natural log of both sides. Now, why the heck would I do that? Hopefully you know before I tell you why. It's because if I have a natural log there, we can bring any exponent out in front. So I can bring that whole thing out in front. Ooh, that's a 4. And I get this. Okay? And what I just did there, I turned practically an impossible problem into a doable problem. Okay? And I turned that function to a function right here, function to a function, into a product rule. And I know the product rule. So the natural log of y is 1 over y. Then I have to take the derivative of y, which is 1 dy dx. And that is equal to, okay, let's go ahead and do this product rule. It would be my u, that's right, times the derivative of my v, which would be 1 over, don't you dare touch the inside, but then you take the derivative of the inside. Oh, snap, that's an inverse tangent. Inverse tangent would be 1 over 1 plus, don't you dare touch the inside squared. But it's an x, and the derivative of x is 1, so that part is done. Plus, okay, let's rewrite my v guy. And then I got to take the derivative, multiply by that derivative of my u, which is e to the something, which would be e to the something. Oh my gosh, this problem is so fun. It like goes on forever. But then I got to multiply that by the derivative of x cubed minus 4, which is 3x squared. I'm sorry, that looks like it's up there as the exponent, but it is not. And then to finish this problem, it is dy dx is equal to, I've got to multiply that y on both sides. I'm going to write it cleaner here. That'd be e to the x to the third minus 4 times, can I make that guy look prettier? I guess I could have put that in the numerator, right, class? I'm going to leave it like this here just so we don't get crazy. I'm going to put these under the same thing. And I could do that if I put parentheses. Plus, I'm going to write this other piece a little bit cleaner. And it seems crazy, but this is 100% acceptable. And there's really no other simplification that I could do. And then I could go times, that'd be 3x squared, e x to the third minus 4. Oh my gosh, so fun. Once again, now, some of us have been struggling a little bit recently. So what I challenge you to do is any of these problems that we did where you were like, Mr. Tanaka, that was kind of tough. Right now, get out a separate sheet of paper and try it again. Go! Bears!